All right, so you want to remember that population growth or decay is compounded continuously. So there's special formulas for that. It's really the same formula. Okay, for the growth formula, n of t equals n sub 0 e to the power of rt. All right, if you can't remember this, or if you have a hard time remembering this, just remember the compounding continuous interest. A equals PE to the RT, the A equals PERT. Okay, it's really the same formula. And n sub 0 is your starting population. E is a number, that's on your calculator. R is the growth or decay rate, just like R is the interest rate when doing the investment problems. And T equals time. Remember, for the time, the units must match the rate. Okay, if they give you the rate per month, you have to write the time in months. If they gave you the rate per year, then the time should be in years. All right, and for decay, it's the same formula except the exponent is negative. Okay, and if you want to remember the A equals PERT formula, same thing, just make the exponent negative. So these two formulas are really the same thing. This one was just for the investments when the interest rate was compounded continuously, but a population growth is also always compounded continuously. All right, example 1. A school district estimates that its student population will grow about 5% per year for the next 15 years. How long will it take the student population to grow from the current 8,000 to 12,000 students? All right, so this here is an example of population growth. All right, and the formula for that, n of t, is going to be n sub 0 e to the power of rt. All right, if you want to use A equals PE to the RT, A equals PERT, since it's easier to remember, you can use that as well. All right, anyhow, I'm going to use the basic formula. All right, n sub 0 is your starting population. It says the current population is 8,000. So your n sub 0 is 8,000. And n of t is how far is the growth at the end of the time period. So this here, n of t is going to be 12,000. All right, 5% per year is the growth rate. So 5% translated to a decimal is 0.05. And the time period is 15 years. So t is going to be 15 years. All right, remember, you want to make sure the units match for R and T. The growth rate is 5% per year, and the time is also in years. So we are okay right there. All right, n of t, that's the ending population, and that's 12,000. And that equals the starting population, n sub 0, that's 8,000. And that's times e to the power of r, which is 0.05. And I made a little mistake. We are not plugging in 15 years for t. Okay, they say the population grows at that rate for 15 years, but we are looking to answer how long will it take the population to go from 8,000 to 12,000. Okay, so since they're asking how long it will take, that will be the t. All right, so let me erase what I wrote here. This is not t right here. All right, t is what we're solving for. All right, so I'm going to put the t right here. And now let's see. We want to isolate t. How do we isolate an exponent? Well, we have to take the log or natural log of both sides. Now, the exponent is only applied to the e. It's not applied to the 8,000. So I want to get rid of that 8,000. This is 8,000 times e. The opposite of times 8,000 is divided by 8,000. Okay, so I'm going to do that to both sides. 8,000 over 8,000 is gone. And you can leave this as is. You can make it a decimal. Okay, just for abbreviation, 1,000 divided by 1,000, we can cancel those zeros. I'm just going to leave it as 12 over 8. Okay, you can certainly make it a decimal, but I'm just going to leave it like that for now. And that equals e to the power of 0.05t. Okay, so all I did so far was plug in for the formula and divide both sides by 8,000 because I'm trying to isolate this right here. And now we said you can use log or natural log on both sides to isolate the exponent. You can use log, but since we have a base e, I might as well use the natural log. All right, so I have to do the same thing to both sides. Remember that the natural log is the same as log base e. All right, so if you take the natural log of a number, that's log base e. So since the bases match here, natural log is base e, and this is an e. Remember, if the base of the log matches the base of the number that has the exponent, it just cancels. So this is log base e, and that's base e, so that just cancels, and you are just left with the exponent. Okay, so we have the natural log of 12/8, and that equals 0.05t. Solving for t, the opposite of times 0.05 is divided by 0.05. All right, it cancels on the right, and I'm going to do this on the calculator. All right, natural log of 12 divided by 8, close parentheses, and that was divided by 0.05. Okay, so this is the numerator, this is my denominator. Click equals. And let's see, I don't think we need 4 decimal places. I'm just going to use 3 for now. So the fourth decimal is a 3. That means I round it down, 8.109. All right, so t rounded off is 8.109, and that is in years. All right, so if you wanted to convert this to months, you would just take the 0.109 and multiply it by 12, or convert it to days, 0.109 times 365. Okay, but it's a little over 8 years. All right, example 2, the population of a certain city in the year 2004. In the year 2004 is about 650,000. If it is losing 2% each year, when will the population decline to 500,000? All right, so this is a population decay. All right, I know you don't generally use the word decay with people, but that's what it is. It's declining. It's a population decay. So it's the same formula that we just used, except the exponent is negative. N of t equals n sub 0 e to the negative RT. All right. Again, same formula if you want to use A equals per, but with a negative RT. That's the same thing. All right, it's just that we usually use this one for investments or banking and this one for population, but it's the same formula. Really, this is the same formula as population growth. It's just the exponent is negative. Anyhow, when will the population decline to 500,000? Okay, so the initial population, n sub 0, is 650,000. And it's losing 2% each year. Oh, okay, so the rate is 2% or 0.02. And that is per year. All right, and when will the population decline to 500,000? This is going to be your n of t. Okay, that is your ending population. All right, so n of t, that's 500,000. And that equals n of 0, your starting population, 650,000. And that's times e to the negative r, which is 0.02, and times t. So they're asking when will, so we're basically solving for t. So it's negative 0.02 times t. All right, so again, we are trying to isolate this exponent here. And this exponent is only applied to the e. It's not applied to the 650,000. All right, so we want to get rid of that. The opposite of times 650,000 is divided by 650,000. On the right-hand side, 650,000 divided by itself, that's gone. On the left-hand side, you can leave it as is or cancel some of the zeros. Here I'll cancel 3 zeros top and bottom, and I'll just leave it as 500 over 650. Okay, I didn't change anything. I just reduced it. It doesn't matter anyway. We're going to be taking the natural log. Okay, on the right-hand side, the 650,000 cancels. I'm going to leave a little space and write e to the negative 0.02t. Now, just like last time, you can do log or natural log, but natural log is better when you have an e as a base. So I am going to do the natural log on both sides. On the right-hand side, natural log is base e, and here we have a base of e, so that cancels, and we are just left with the exponent. Okay, in case you don't understand what happened there, this ln is the equivalent of log base e, and we have e to the negative 0.02t. All right, so log base e and e cancels, and you're just left with the exponent. Anyhow, almost done. ln of 500 over 650 is going to equal negative 0.02t. The opposite of times negative 0.02 is divided by negative 0.02. Okay, on the right-hand side, it cancels, and you're left with a t. And the equal sign, well, it's going to be squiggly lines because we're going to end up rounding off. I am going to do this on the calculator. ln of 500 over 650 divided by negative 0.02. All right, hit clear. Natural log of 500 divided by 650. Close parentheses, and that whole thing is divided by negative 0.02. It equals, and we get 13.118 rounded off. All right, so the units were in years. So that's basically it. Again, if you wanted days, take the 0.118 and multiply it by 365, and you'll get 13 years and however many days. All right, last one. It says at 2 o'clock, a culture contained 3,000 bacteria. They are growing at a rate of 150% per hour. When will there be 5,400 bacteria? All right, so once again, we have a population growth. So at 2 o'clock, the starting amount is 3,000. That's going to be your n sub 0. All right, and the rate is 150% per hour. So the rate R, if you take 150% and you move that decimal over 2 places, that's 1.5, or you can say 1.50 per hour. All right, notice it says per hour, so I just wrote hour in the denominator. All right, and finally, when will there be 5,400 bacteria? Well, that is going to be your n of t. All right, so we said the formula is basically the same as A equals PERT. I'm going to write it the normal way, or the official way, I should say. N of t equals n sub 0 times e to the power of RT. However, if you like, you can use A equals PERT, okay, if that's any easier to remember. Like I said, this is usually for monetary investments, and this is for the population. They're the same formula anyhow. All right, so n of t is your final amount. That's 5,400. N sub 0 is your initial amount, and that is 3,000. And that is times e to the power of r, which is 1.50, times t. Okay, recall that we said the units on r and t must match. So since we did the rate per hour, the time t is going to be in hours. Okay, and however many hours it takes, we're just going to have to add that amount to 2 o'clock. Anyhow, we're solving for t. All right, and we want to isolate this exponent. Okay, the exponent is only applied to the e, so we want to get rid of the 3,000. The opposite of times 3,000 is divided by. All right, I'm going to do that to both sides. 3,000 over itself cancels. All right, we want to isolate this exponent. The exponent has a base of e. So which of the logs is base e? Well, log base e is the same as the natural log. Okay, so I'm going to do the natural log of e to the 1.50t. And I'm going to do the natural log of 5,400 divided by 3,000. All right. I suppose you can do a decimal here if you like, but if it's a repeating decimal, you don't want to do that. Okay, you leave it as a fraction if it's repeating. Anyhow, on the right-hand side, this is log base e, this is base e. Those cancel. You are left with the exponent. Okay, so we have ln 5,400 over 3,000. And that equals 1.50t. 1.50 times t. The opposite of times, 1.5. is divided by 1.5. Cancels here. Do this on the calculator. Okay, you can cancel the zeros at least. Divided by 100 top and bottom, it's 54 over 30. ln of 54 over 30, whole thing divided by 1.5. All right, ln of 54 over 30, close parentheses, that whole thing is divided by 1.5, hit equals. I'm going to do 3 decimals. We're looking at 0.392. All right. All right, 0.392. Recall that we said the units were in hours. All right, so that's T's approximation, but they said when will, I'm assuming they mean what time. Okay, let's see how many minutes that is. 0.392 hours. If you do 0.392 times 60, I'm going to round off to the nearest minute. All right, that's 24 minutes. So if we started at 2 o'clock, and this process took 24 minutes, it will occur at 2:24. All right, they didn't say AM or PM. They just said it started at 2 o'clock, and when will it reach 5,400? So this was a population growth. It took 24 minutes to grow when we started at 2 o'clock. So at 2:24.